This was your assignment question, and the answer is to another mirror. And you can see the problem. This ray is going like this, and if you take any other ray, it has just no hope of reaching the eyes. This point was the best hope point, and that point is not working. Now the question is changing the location. Will it work? On the right side, you can see that distance has been changed. But even now, the problem is identical. Whatever this person could see, Neil, same situation is here, Neil only. Beyond that, it doesn't work. Now this can be easily seen if you I think I would go to the whiteboard. If this is E for I, and if this is K for me, then exactly the same situation will happen if you change distance. Just draw a straight line. Which is acting as normal. These two angles have to be equal, and these two angles will also have to be equal. Then why should it go somewhere else? Why should it go here? This can't be correct, isn't it? Because these two must be equal. So it has to go there only at E. Let me know if you have any questions. Imagine some ceiling or roof and a light source is hanging from the ceiling. Okay, there's some ceiling here. This is a light source. There is a plane mirror on the wall. This is the mirror on the wall. Somebody walks along this line. The greatest distance over which the person can see the image. The greatest distance over which the person can see the image of this in the mirror. How can it be D? This is the light source. Its image is formed here. If I am here, I can see it. If I am here, I can see it. It has to be more than D. In other words, I will get these rays, isn't it? Here also, yes, very much possible. So this D is very much possible, but beyond this D and that side also, that side also. Well, how do I know that you mean option D? You are using small letters. Let's find out how much is this. This is L. That is also L. I'm just doing one construction. This fellow. So this is L. If you compare this triangle and this triangle, then what do you find? Angle, 90, 90. From angle similarity, these are similar triangles. 90, 90, angle. So when we are talking about similar triangles, then L upon 2L should be equal to D by 2 divided by whatever this fellow is. Let me call it X. And that means X is equal to D. So this D, then this D, and the other side also D should be there. So 3D should be the answer. Any questions? Let me know. If you want, I can give you the options. Looks like a coordinate geometry question. So it should pass through this point 1 comma root 3 after reflection. So we can construct a normal here, and then we can construct the mirror like this. This should be the mirror. Yes, any answer? This angle is 60. These are 30, 30. This will be 60, 60. Since 120 is not given, I think 60 should be the best choice. If there are any questions, then let me know. Alright, this is the plane mirror. Half of it is covered with black cloth. This is covered with black cloth. Object is right in front of this half. Eye is here. The question is, can I see the image of the object? You have to give only one of the two answers. Yes, tick mark. No, cross. Can I see the image of the object? Yes for tick mark. No for cross. Half is covered, not full. This is gone, half. This is as good as no plane mirror. But this plane mirror is very much there. How about this? So, yes is the correct answer. Yes, it is B. If you would like this to be discussed, raise your hand. Moving on to curved mirrors. Imagine some ball sphere which is hollow from inside. So a spherical shell. Make a cut of this type from that spherical shell. Spherical shell has a center and it has a radius. This center is important for us also. We normally call it C. So this center is called C and the geometrical center is called pole. This is a geometrical center called pole. The line joining pole to C and extend it is called principal axis. If reflection is from this side, then it's called concave mirror. The radius is the same shown here. This radius is also important for us. After cutting, of course, you need to do the coating so that reflection predominates. You want reflection. So something like silver coating. For convex mirror, other things that I said, pole, C, R, principal axis, those concepts are similar, but reflecting surface is different now. And you can choose how to coat, making this reflecting or that reflecting. Now, the laws of reflection are the same. So you take some incident ray, you choose wherever you want it to hit. Then at that point, you construct a normal. How would you construct the normal? You know that normal passes through C. So it would look something like this. That would be normal. And then it is the same story, angle I equal to angle R. Let me see if I can join it here somewhat. Angle this equal to angle that. Same story of flowing mirror. Here also, in case of convex mirror, this would be a normal. So these angles must be. It's very easy to construct normal because it has to pass through C. Now in case of convex mirror, this is a reflecting side. That means rays would not exist here. So in center of curvature C is behind the mirror. In case of convex mirror, no rays exist on this side, but C does exist on that side. Now you have to answer this question. An organic chemistry student accidentally drops a glass marble into a silver nitrate mirroring solution, making the outside of the marble reflective. What kind of mirror is this? How can it be flat? It's a curved surface. Reflection will be like this type, meaning this type. So it's going to be convex mirror. Option 2. Now, let's talk more about concave mirror. We just saw one ray going to the right and then coming back. That's because it was traveling along principal axis, and principal axis is a normal itself. So if a ray travels along the normal, it has to bounce back. Whenever you send a ray along normal, it will just bounce back. Any normal issues, it just bounces back. But if you take something like what we saw just now, a ray which is parallel to principal axis, then to know from where it is going, you need to construct a normal and then apply the law of reflection, angle I equal to angle R. And then you find it's going through some point on the principal axis. That is an important point for us. If this is a parallel ray, parallel to principal axis, because if you take any other ray also which is parallel, then interestingly goes through the same point. Please note that we will be confining our discussion to paraxial rays. Paraxial rays are those rays that are close to the principal axis. So you may be seeing them farther in this drawing, but actually these rays are supposed to be close to the principal axis. So our discussion would be limited to paraxial rays. So this ray also goes through the same point. It's parallel. And likewise, if you take another one and another one, as many as you take, this point is an important point. And it's called focus of the concave mirror. It's a point where rays actually meet. They actually cut. Okay. Rays that are parallel to the principal axis all reflect, so they pass through focus. I have already said that we will be limiting our discussion to paraxial rays. What you see here near the principal axis, that's what it means. Near the principal axis, that's paraxial ray. Now we define something important. Distance from this pole or the center of the mirror to S. That's called focal length. Now at this point you take it that f is r by 2. We will be proving it when we do the mathematics. Now concave mirror is like a concentrator. Rays that come from the sun, they can be treated as parallel rays because they are coming from so far. They can be treated as parallel rays. Otherwise, if you take a point source, then it sends light in this way. Point source, it sends light in this way. But if you see that from a large distance, then the rays that come towards you, they can be treated as parallel rays. So parallel rays will be made to go from a point and their energy will become significant, so much that it can start a fire. And of course, this should be equal to focal length, this distance. In optics, we have a principle called as the principle of reversibility of rays. So when we say that parallel rays are made to go through the focus, then if you keep the source of light at focus, then rays will hit the mirror and then they will become parallel. I repeat, parallel rays meet at a point called focus. There is a principle of reversibility of rays. If you keep the light source at the focus, pointed light source at the focus, then light from it will hit the mirror and will become parallel to the principal axis. So we will make use of that concept and see how that match stick can be burnt. We use two mirrors here. We will use some light source for the left mirror, and we will keep that light source at its focus. Here it comes. Now light rays will come from that light source, they will hit the left side mirror and they will become parallel. Right? Rays traveling through focus before hitting mirror are reflected parallel to principal axis. Now, imagine parallel rays hitting the right side mirror, and when parallel rays hit the right side mirror, they go through its focus. And at its focus, there is a match stick. And there is a concentration of energy when you concentrate rays, you are concentrating energy. So it burns. Any questions? Let me know. In case of convex mirror, if you take a ray like that, it's trying to go towards C, it will just bounce back. This is normal. So this bounces back. Now if you take another parallel ray, parallel and paraxial we are discussing, then where will it go? For that you need to construct a normal. So that normal would be, you will have to join these and further angle I equal to angle R. So that's how you will get this line accurately. And you can take several such parallel lines and you find something interesting, that now first of all they are diverging, they are running away. Look at the angle between them. They have no intention of meeting somewhere on the left side. But if you imagine them extending, then they appear to meet on the right side, but they don't travel to the right side. So no question of their actually meeting. It's all appear to type of situation. And where they appear to meet, that's called focus. So that's focus. Where parallel rays appear to meet. We are talking about paraxial rays. So that distance is focal length from the pole to focus, and we'll be proving it when we do mathematics, that it is R by 2. We can also take rays downwards, that's no problem. It will be the same story. Any questions? Let me know. No assignment for today. We stop now.